Hi folks, Chris McClure here. We're going to do a quick review of inequalities and then talk about how to solve uh, inequality statements involving variables. Okay, so to start off with, let's just review what an interval is, because the solution to an inequality will usually involve intervals. So what is an interval? An interval is just basically some collection of real numbers that's greater than or equal to or greater than one number and less than some other number. Now, if we want to talk about the closed interval between A and B, as in, like, for example, from 1 to 3, we're talking about all the numbers that are greater than or equal to A, but less than or equal to B. And this is a symbology using the closed square brackets to indicate that the endpoints are included in this endpoint, or in this interval. Now, if we want to indicate the set of numbers greater than A but less than B, not including A, not including B, then we would use this notation there with the open and closing parentheses, where we have that set of values for x less than A less than B but greater than A. When we have a half open interval, which means the same thing as half closed interval, that means that one endpoint is included but the other endpoint is not included. So, for example, the set of numbers greater than A but less than or equal to B would be indicated with this sort of notation. Or if you like, inequality symbols using that notation. For example, or if you want to take a look at the set of numbers greater than or equal to A but less than B, then there's the notation for that one. Or here's the inequality using the inequality symbols. Okay. Now, if you have an inequality involving infinity, then you will use the infinity symbol to indicate an endpoint, but you will never use a square bracket to indicate that you are actually including infinity, because the infinity is not the set of real numbers. Okay? So this first one right here, that's the set of numbers greater than or equal to A. Period. The second one here, that's the set of numbers greater than A. Period. This third one, that's the set of numbers less than or equal to A. Period. This fourth one, that's the set of numbers less than A. Period. And then this last one here basically means all real numbers. We oftentimes will like to graph our intervals using a real number line. We want to graph the set of numbers greater than A but less than B, then we could do that by locating A, locating B, and then placing opening and closing parentheses on A and B like you see here, and then shading that portion of the real number line between A and B. Here's the closed interval from A to B with the little square brackets on A and B respectively. Here's your half open interval greater than or equal to A, less than B, all right, with the respective closed bracket and open parentheses. Here's the half open interval greater than A, less than or equal to B. Here's the interval greater than or equal to A with that square bracket on A, but it shades all the way to the right. And you typically will just go to the end here, or maybe put a little arrowhead at the end to indicate that you're going on forever to the right. Or if you're not including the A end point, you'll just put a little open parentheses there to the left. Same discussion when you are talking about the set of numbers less than or equal to A or less than A. And then finally, the whole set of real numbers, you just shade the real number line. All right? Now, We are now going to talk about expressing inequalities. Some of them are double inequalities, some of them are single inequalities, using interval notation. So when we talk about x less than or equal to 4 but greater than or equal to negative 2, we're talking about this set of numbers here with this notation, with the square brackets, by the way, because the square brackets correspond to the mixed inequalities less than or equal to. Or the set of numbers greater than 2 but less than 7. So here we are, we're going from negative 2 to 7 with the open parentheses. The set of numbers greater than or equal to 6, so we'll just have the square bracket with the 6, comma, infinity, closed parentheses there. Or for part D here, x less than or equal, or x less than negative 3, that's just going to be given this notation there with the open parentheses associated with the negative 3. So any number that's less than negative 3 will be in this inequality. The negative 3 itself would not be in the inequality, but any other real number less than negative 3 will. So negative 4, negative 5, etc. Going in the other direction, here we've got the interval from negative 1 to positive 2, including 2, but not including negative 1. So we would have this interval notation. And likewise, as we go on down here too, we've got the interval from negative 2 to 0, inclusive, both endpoints. The next one, we've got x greater than 5. All right, then this next one, we've got x less than 1. Okay, here we go. We're going to now talk about how with inequalities, when we go about trying to solve an inequality, we'll have to go about performing certain operations to both sides of an inequality. But not all of the rules apply to inequalities as they do for equalities. But most of them do. So for example, for an equality, if I were to say that x is equal to 2, and if I were to take the square of both sides, then this would also be a true statement. Same discussion with inequalities, except the fact that we know that any negative number squared would be a positive number. So it's true that negative 2 is less than or equal to 0. But if I were to square both sides of this equation, then I have this true statement there that 4 is greater than or equal to 0. So if I have the statement that I have some real number a, that when I square it, the result is going to be a positive number, unless a is 0, which would then we would have 0 equals 0, which is also a true statement. So we have this true statement always. The square of any real number is non-negative. Okay. If you have an inequality and you add both to both sides the same number, then the resulting inequality will still be true. And you could also subtract the same amount as well. But just focusing on addition, let's look at this example here. If x is less than negative 5, and you add 5 to both sides, then you have x plus 5 is less than or equal to 0. Or if x is greater than 2, and if you were to add negative 2 to both sides, then you would have x minus 2 is greater than 0, which is an equivalent statement. So when you add the same amount to both sides, you have an equivalent inequality that is still true, provided that the original inequality was true. But hold on, let's go back here. But if I say that x is less than negative 5, that is a statement. It may or may not be true. Depends on x. if x is some number less than negative 5, then it is a true statement. But if x is greater than or equal to negative 5, then that would be a false statement. Same discussion as in the inequality that is equivalent to the original inequality. We can multiply both sides by the same positive number and have the same solution set. In other words, you have an equivalent inequality. So, for example, if I have 3 less than 5, we know that that's a true statement. And if you multiply both sides by 2, you get 6 is less than 10, which is also a true statement. But if you multiply or divide by a negative number, then that switches the direction of the inequality. All right? Because we will end up with negative 6 and negative 10. What's the relationship between those two numbers? We know that negative 6 is greater than negative 10. Whereas the original inequality was that 3 is less than 5. So when you multiply or divide by a negative number, that switches the direction of the inequality symbol. Okay? Always remember that, folks. So this right here summarizes the multiplication properties for inequalities. This basically reminds us that if we multiply or divide by a negative number, that switches the order of direction of the inequality. So here's some examples. If we have 2x is less than 6 and we want to isolate the x from the left-hand side, we'll have to divide by 2. Or in other words, multiply both sides by 1/2, which will give us x is less than 3. Or if we have x is divided by negative 3, which is greater than 12, to isolate x, we'll multiply both sides by negative 3. But when we do that, that switches the direction of the inequality. So that'll give us x less than negative 36. And notice that the direction of the inequality switched. If you have negative 4x greater than negative 8, then you divide both sides by negative 4, which will reverse the order or the direction of the inequality, giving us x is less than 2, which is the equivalent inequality to the negative 4x greater than negative 8. Also, if you have a negative x less than 8 and you want to get rid of the negative symbol, then you can multiply both sides by negative 1, which again will reverse the direction of the inequality, giving you x greater than negative 8. Moving on here. Also, taking reciprocals of both sides will preserve the direction of the inequality. So, for example, we know that 2 is greater than 0. So if you were to take reciprocals of both sides, well, 1/2 is still a positive number. However, we know that negative 3 is less than 0. If you were to take reciprocals of both sides, we know that negative 1/3 is still less than 0. So if you have an inequality where 0 is on one side of the inequality, then taking reciprocals of both sides preserves that direction of inequality. All right, moving along here. So we're going to talk about solving inequalities here by basically going through the same sort of process that we did with equations. You can rewrite your inequality by a sequence of equivalent inequalities by adding the same amount to both sides, subtracting the same amount from both sides, multiplying both sides by the same number. And again, remember, if you multiply both sides by a negative number, that switches the direction of the inequality. And same discussion with division. Okay, so you do that sequence of steps until you get x on one side of the inequality and a less than or greater than or less than or equal to or greater than or equal to sort of symbol on the other side. Okay, so all of these steps apply here. Moving along here. So let's do some problems here. We've got 5 minus 3x greater than or equal to negative 1. So think about what we need to do to isolate x. How about we subtract 5 from both sides? This 5 right here. So that'll be one step closer for us to solve for x. So subtract 5 from both sides, and that'll give us negative 3x greater than or equal to negative 6. Because minus 1 minus 5 is minus 6 on the right side. And then divide both sides by negative 3, which, by the way, will reverse the order of the inequality. And on the right-hand side, negative 6 divided by negative 3 is 2. So you've got the equivalent inequality, x is less than or equal to 2, which is the same as saying the original inequality. Okay, and then we have our solution set. You can express your solution set using that set builder notation like that, or you could use that interval notation, or you can even graph it using the real number line, placing that square bracket at 2 and then shading to the left. Okay? Here we have our next example, 4x plus 3 less than 2x minus 1. Okay, so remember we're going to get our variable terms on one side of the inequality, our constant terms on the other. So maybe we could subtract 3 from both sides, because we typically like to have our variable terms on the left and our constant terms on the right. So we'll subtract this 3 right here from both sides. All right, and then maybe subtract 2x from both sides, and then divide both sides by 2. And because of the fact that we did not multiply or divide by any negative numbers, the direction of the inequality stays the same, leaving us with x less than negative 2. So any number less than negative 2 will satisfy this inequality. And indeed, if you were to plug in, say, for example, x is equal to negative 3, if you were to plug in negative 3, well, that is a number that's less than negative 2. For example, and you'll plug that in for x, you'd have 4 times negative 3 is negative 12, plus 3, that's negative 9, less than, and then 2 times negative 3 is negative 6, minus 1. And so what do you have? You have what? Negative 9 less than negative 5. And that's the true statement. For example, I'm not saying I'm checking the solution. I'm just checking to make sure that it makes sense, though, by plugging in some number from the solution set. For example, negative 3, to see that the inequality really is true for some number from the solution set. Okay. All right, and by the way, here is the shaded portion on the real number line where we had put a open parentheses facing to the left at negative 2 and then shading to the left. Now, negative 2 is not in the solution set, because if you were to plug in 2 for x in the original inequality, that would be the same thing as saying 0 is less than 0, which is not true. But any number less than 2 will solve the inequality. Let's now talk about solving inequalities that are combined into like a double inequality. So here's an example of such a combined inequality, sometimes called a double inequality. Now, you could break it down into 2 separate inequalities like this one, because after all, this double inequality says that 3x plus 2 is greater than negative 1 and less than 5. So you could just write it as 2 separate inequalities, go through your solution process for the both of them. On the left-hand side, we end up with x is greater than negative 1. And for the second inequality, you go through the same sequence of steps, essentially, to solve for x. And you see that x is less than 1. And you could put them together to say that x must be greater than negative 1, but less than 1. So here's your solution set. Any number between negative 1 and positive 1, not inclusive, will work. But by the way, here's your interval on the real number line. But you could actually go through, let me go back. You could actually go through here, and let me just go back to the original double inequality. Instead of solving it like we just did, you could just go through, instead of breaking it into two separate inequalities, just go through and do what you need to do to solve for x, to isolate x by applying the same operation across both inequalities. So for example, you could subtract 2 throughout the two inequalities. And on the left you have -1 minus 2 is -3. You have 3x less than, and then 5 minus 2 is 3. And then you could divide by 3 on both sides of these inequality symbols. On the left, you have -3 divided by 3 is -1. And on the right, you have 1. So it's a lot simpler than that sequence of steps that we just went through, okay? Instead of breaking it into two separate inequalities, just solve it as one combined inequality. So suppose that we've got this double inequality. Go through that same sequence of steps. Maybe multiply throughout by 3 to kill off this denominator of the fraction there, and then maybe subtract 5 from both sides, from both inequality symbols, to get rid of this 5 right here, and then divide throughout by -2. And remember, when you divide through by -2, that reverses the direction of the inequality symbols, giving us 1 greater than or equal to x greater than or equal to -2. Now, at this point, you could decide to reverse the direction of this inequality to where it reads more like this, where you're going from smaller to larger. After all, 1 greater than or equal to x greater than or equal to -2 is the same thing as saying -2 less than or equal to x less than or equal to 1. And it's more natural to write it the second way. Then, of course, you could write your solution set either in the set builder notation or the interval notation, or as a shaded interval on the real number line. Moving along here. Suppose that we have this inequality here. 3x plus 6 to the -1 power greater than 0. Now, that means 1 over 3x plus 6 greater than 0. Now, using the reciprocal property, that means the same thing as saying that 3x plus 6 is greater than 0, which we know how to solve, because 3x plus 6 is greater than 0 means that you subtract 6 from both sides and then divide both sides by 3, and you've got your solution. Okay? So we already walked through there. All right. We could also do this crazy trick where you start off with this simpler inequality, and then we can kind of work backwards to find out what you need to do in order to get a certain expression in the middle of that double inequality. So, for example, if x is greater than -3 but less than 2, then what would a and b have to be so that this inequality is true? Well, it looks like for x, we multiply by 3 and add it 2. So for -3, we can multiply by 3 and add 2. And that gives us -9 plus 2 is -7. And also this 2 right here, you could take 2 and multiply by 3. So 2 times 3 plus 2 is equal to 8. So a would have to be -7 and b would have to be 8 in order for this inequality to be true. So that's what we're doing there. Okay? So you'll see at least one homework problem asking you to do the same sort of sequence of steps. All right, we have one last problem to take a look at. This is an application problem, code word for word problem. But hey, this is easy, folks. We know that in electricity that the voltage is going to be the current flow times the resistance in a circuit. Here's the equation. E is equal to IR. E is voltage, I is current, R is resistance. Now, suppose that we have our voltage between 110 and 120 volts. We have a resistance that's equal to 10 ohms. So what is the range of values for the current, I? So we could start off with this equation or this inequality that says is that the current, that is that the voltage is between 110 and 120 volts. It replace E by IR and then replace R by 10 and then divide through by 10 so that you've got I between 11 and 12. As in the current that's being drawn by this air conditioning unit is between 11 and 12 units of current, amps. Okay, so that's how you solve that sort of inequality, is just write the original inequality and then solve it for the desired quantity. Okay, so that's it for today. I'm going to follow this up with a separate recording on how to solve equations or inequalities involving absolute values. Okay, so take care, folks. And I will see you later.